To start off our discussion of intermolecular forces, I asked students, why can a gecko climb up walls? A lot of students wrote in responses or chimed in. I have a student in one of my classes who has an animal actually similar to a gecko, who shared with us that this is largely because of the special features on a gecko's hand or feet that would cause it to be able to stick to that wall. So now we'll take a look at the toes of a gecko. So here's some microscopic images to zoom in on these toes, and we'll see here that they're covered in millions and millions of microhairs, and these are called setae. And at the very end of these microhairs, we've got a flattened portion. That's what the last image is kind of showing us there. It flattens out, and that's actually called a spatulae. So it kind of looks like a spatula, maybe where they got that name from. But this flattened portion is going to be the portion that is essentially sticking to the wall. And why it's able to do that is due to intermolecular forces. We're going to talk about these today, but essentially an intermolecular force exists between all molecules. It's not a very strong force though, but what allows the gecko to be able to stick to walls then is that this happens millions and millions of times. So each one of these spatulae at the end of this microhair is experiencing this force, and if that is multiplied over again millions and millions of times, that's what allows this gecko to be able to effectively walk up walls. This is what I had just clarified on that last slide, that the gecko's feet do have these millions of microhairs called setae, so you can see there how it's spelled, and that these tiny, tiny hairs end in that flat tip called a spatulae, which sticks to the walls due to intermolecular forces. So that is our topic for today, is intermolecular forces. Our standard for this lesson is that we will understand that intermolecular forces created by the unequal distribution of charge result in varying degrees of attraction between molecules. We're going to compare and contrast intermolecular forces, including hydrogen bonding, dipole-dipole bonding, and London dispersion forces within different types of simple substances. Finally, we'll predict and explain their effect on chemical and physical properties by using models or graphical representations. So first we need to clarify some definitions here. And these two words are often confused, intra and inter. And they're really actually prefixes that we'll put in front of other words. So when we see intra in front of another word, it means that it's within or inside one group. On the other hand, inter means that it's between two groups. So the best example that I've got for intra would be like intramural sports. So many colleges have intramural sports, and these would be people that want to play sports but aren't on like the varsity teams. The varsity team would play against other colleges and universities, but students who still want to play football or soccer can play on an intramural team, and they'll play against other students still from that same university. On the other hand, inter is between two groups. So the best example of this that I've got is the interstate system. So interstates, if you drive on them, can take you to other states. You can leave Tennessee on an interstate because they connect it between multiple states. I always found it funny though that there are interstates in Hawaii, which you can't actually connect those interstates to another state, so it kind of defeats that definition there. So now let's look at these prefixes and attach them onto our molecular forces that we've been looking at. So intermolecular force means, again, it's between two groups, and specifically between two molecules. We know that molecules are covalently bonded groups of atoms, so we're looking at the force that is between two groups of covalently bonded atoms. So in this picture there on the left, the intermolecular force would be that dotted line. So I'm going to circle that for us here. That dotted line is what we're talking about. What is going to connect one water molecule to another molecule. And this is in contrast to intramolecular forces. So that's what we've been talking about so far when we talk about ionic and covalent bonds. So those are both interactions that are happening within a compound or a molecule. So that is taking two or more atoms and creating something new from it. That's an intramolecular force. So that's what we've so far been talking about up till this point, but today we're going to turn our focus to the intermolecular instead. Here's another picture to illustrate that difference between intramolecular and intermolecular. So intramolecular is, again, what we've been talking about, that we have one atom of something connected to another. So here we've got chlorine bonded with hydrogen. And so we've got that bond here in the center, and that is an intramolecular attraction that's holding them together to create something new. But each separate molecule of hydrogen bonded with chlorine is going to be attracted to other molecules through the intermolecular attraction. So there's a couple different types of this, and we're going to look at these different types today. Before we can talk about the different types of intermolecular forces, we also need to look at the definition of a dipole. And we've talked about this concept, but without really using the name dipole yet. So let's relate it to what we have been talking about. So a dipole is going to be caused by an unequal sharing of electrons in a covalent molecule. So we know that in a covalent molecule, we have two atoms that are sharing their electrons rather than transferring them. But sometimes one of those atoms wants the electrons a little bit more than the other one. That one we say is more electronegative. So as that happens, it's going to kind of hog those electrons, keep them closer to that more electronegative atom. And as that happens, then the positive and negative charges are going to separate to two different sides of that molecule. So essentially the area that's got the electrons, the one that's hogging the electrons, is going to have a more negative charge. And the atom that is not hogging the electrons is going to have a partial positive charge. And we call that net electrical charge a dipole moment. So there's three types of dipoles. Our first type is a permanent dipole, and these are the ones that we're most familiar with. These we have found in polar molecules, and they're what I was previously talking about on that last slide there, where we have one atom that is hogging the electrons. So in this picture down below, we've got hydrogen and chlorine bonded together covalently, and then above them we've got this lowercase delta symbol. And that's next to either a positive or a negative sign. So that's telling us that hydrogen has a partial positive charge and chlorine has a partial negative charge. Again, that's because chlorine's more electronegative and it's hogging the electrons, which are negatively charged. So that's going to create this permanent dipole. It always exists that chlorine's going to be more negative than hydrogen would be. This is in contrast to instantaneous or induced dipoles. So instantaneous dipoles happen temporarily based upon the location of electrons within an atom. So in this example below, we've got a helium atom, and helium's going to have two electrons, and those two electrons are just kind of floating around in that electron cloud model. We talked about that when we talked about atomic theory. And that those electrons, even though we draw them in certain orbitals and positions, they really can exist in a lot of different spaces there around that nucleus. So in this example, they are just happening to be on the same side of that atom. And what that means now is that that atom really has separate charges even within the single atom. So the one side that has the electrons is experiencing a partial negative charge, and the other side is going to have a partial positive charge. Now, if this atom goes near another atom, it's going to induce a dipole on that other atom. So induce essentially means to make happen. So people, you've probably heard the word maybe with inducing birth. Sometimes women go into labor and they induce. Essentially, they make the birth happen due to chemicals that they can give the mother. So same kind of here is that we are making this dipole form due to it being next to an instantaneous dipole. Okay, so those are our three types of dipoles that we'll need to look at moving forward. So one of the cool things about dipoles is that they are vector quantities, and as such they're able to cancel each other out. again, due to this unique nature of being a vector. So you might have seen a vector in math class, and I asked the class, what makes a vector a vector? And pretty much in comparison to a line versus like a line segment, what would make a vector be considered a vector? Yeah, so a vector is going to have direction and magnitude. So when we say it has direction, it's pointing a certain way. It has a certain direction. Magnitude really means that it has a certain value associated with it. In math class, when you were looking at vectors, you usually would just represent this by how long you've drawn it. And sometimes that would have a numerical value attached to it. With chemistry, our magnitude is really going to represent the polarity of that bond. And then we'll still use the direction to point which direction those electrons are actually moving. So let's return to our example of hydrogen covalently bonded to chlorine. So in this example, we know that chlorine's more electronegative, so it's got that partial negative charge written above it, and hydrogen, therefore, is going to be a partial positive charge because chlorine's hogging those electrons. So we can represent this with a vector to show the dipole moment. So when we do this, we're going to draw an arrow. And just like this is illustrated here, I'm going to show you how I would draw it too. You're going to draw the arrow so that it is pointing toward the direction the electrons are going to go. So the electrons are going to the more electronegative one. They're going toward chlorine. So we're going to point it toward chlorine. And then we're going to add another line over the one that is going to have a partial positive charge. And we're going to add this line perpendicular so that it's kind of indicating to us that that is the one that has the partial positive charge. So this is how we'll add dipoles onto molecules to show the dipole moments specifically within those molecules. So the magnitude and direction of a dipole moment is super important because it tells us whether or not that molecule is polar or nonpolar. So we've seen a couple ways where we can have nonpolar molecules before. That's where we have a nonpolar bond. Maybe that's between two atoms that are the same. So like in this first example here, these pictures, we got nitrogen with nitrogen, hydrogen bonding with hydrogen, or chlorine with chlorine. Those are nonpolar. They're bonding with themselves, so there's no difference in electronegativity, and those electrons would be shared equally. On the next example, we've got methane. That's carbon bonded with 4 hydrogens. That one's also nonpolar, and the difference in electronegativity there is pretty small. So that's why that one, those electrons are also being shared pretty much equally. So those, again, the electronegativity of carbon is 2.5, hydrogen's 2.1, so that comes out to 0.4. So small difference in electronegativity. Carbon's not going to hog those electrons, neither would hydrogen. In our next example, though, we've got carbon bonding with 2 oxygens. And that's carbon dioxide. And this one does have polar bonds in it, because we've got the difference in electronegativity between carbon and oxygen is pretty high. We'll look at this one in another slide as well. But carbon is, again, 2.5, and oxygen is 3.5, so that's a difference of 1. So those are going to be polar bonds between carbon and oxygen. However, it's a nonpolar molecule. So the whole thing is nonpolar because our vectors are going to add up to 0, which means we're not going to have any net dipole moment. So those are 3 different ways that we can have a nonpolar molecule. We're really going to be focusing on the last one today, where we can still have polar bonds within the molecule, but the whole thing is nonpolar because the polar bonds cancel each other out. Okay? On the other hand, a polar molecule occurs when our vectors do not add up to 0. So there is going to be a net dipole moment. So in a polar molecule, we'll end up having a slightly positive end and a slightly negative end. So a great example of a polar molecule is water, and that's what we've got shown here below, H2O. So in this, oxygens are more electronegative. So oxygen is going to want the electrons. So if we were to draw a dipole, it's going to point toward oxygen. We'll have two dipoles, one from each hydrogen to oxygen. And then we're going to add a line perpendicular on the end to show that our positive side is the hydrogen side. So our dipoles, again, are going to point, both of them, toward oxygen, showing that oxygen is our more electronegative. So these are not going to cancel out. Instead, we are then having a slightly negative side of this molecule near the oxygen, and then the hydrogens would exhibit a partial positive charge. So let's look at that example of carbon dioxide again. So we said carbon dioxide is kind of a funny one in that it has polar bonds, but the whole thing is nonpolar. So let's look in more detail at that. So carbon dioxide, again, if we were to write its formula, it would be CO2. And we first need to look at its electronegativity. So the electronegativity values of oxygen is 3.5 and carbon is 2.5. We subtract that out to get our polarity of the bond, and we get a value of 1.0. We've been looking at that chart that shows us what type of bond forms based on the electronegativity differences. And if we were to look at that chart, we would see that this does list that it is a polar bond. And now we would draw our dipoles. And so we've got the first one already drawn on here for us, that we would draw it toward oxygen. That's because oxygen has our higher electronegativity. So that means the electrons are going toward oxygen. So we're going to draw it from carbon toward oxygen. And we're going to do that on both sides. The arrow will point toward oxygen. And then we draw a little line perpendicular near the carbon to indicate that that's our partial positive charge. So now we have arrows drawn on both sides, our vectors pointing to oxygen, both from carbon. And now we have to see if this is going to be a polar or nonpolar molecule. And to do that, we have to do some vector addition. So for our vector addition here, we would notice that both of those vectors have opposite directions. So remember, a vector has a magnitude and a direction. So in these examples here, the magnitude is the same. Both of these are bonds between carbon and oxygen, and both of them have bond polarities of 1. However, they have opposite directions. So we can essentially say that one is going to be considered a positive one and one is considered a negative one. So when we add those together, they will cancel out and equal 0. So we have no net dipole moment, and this is then going to be a non-polar molecule as a whole. Again, even though it has polar bonds, but because those do cancel out, it's going to make a non-polar molecule total. Okay, so now we have another example that I asked students to choose whether or not it is polar or non-polar. So we've got carbon tetrafluoride here, carbon bonded with 4 fluorines with covalent bonds, and the dipoles are already drawn in for you. So fluorines are more electronegative between fluorine and carbon, so therefore the dipole moments are shown drawn facing toward fluorine. The arrows show where the electrons are going, and the electrons would be nearer to fluorine than carbon because fluorine's more electronegative. That means fluorine's going to have a partial negative charge, and carbon, left there in the middle, carbon's going to have a partial positive charge. So now we need to figure out if it's going to be polar or nonpolar. So the main things that we need to look for is the magnitude and the direction. And carbon tetrafluoride is going to be nonpolar, and that's because these dipoles will cancel out. And they're going to cancel out because the magnitude is the same. So the bond between carbon and fluorine is the same magnitude as the bond between carbon and fluorine over here. They're just opposite directions. And because they're opposite directions, we can cancel them out. So this one here on the left would cancel out with the one on the right, and the one up top is going to cancel out with the one here on the bottom. So these will all cancel out and therefore create a non-polar molecule as a whole. So again, even though we have polar bonds within the molecule, the whole thing actually is nonpolar because they cancel out. So let's look at another one. This is phosgene, which is carbon bonded with 2 chlorines and an oxygen. So we'll want to use this electronegativity values given to us in the periodic table to the right to solve this one and see those different bond polarities and magnitudes. So first we'll find all the elements we need. We've got carbon, oxygen, and chlorine. So our bond polarities, the difference in magnitude between carbon and chlorine is going to be 3.0 for chlorine minus 2.5 for carbon equals a difference of 0.5. So that's for each of the ones there at the bottom, 0.5. For oxygen though, oxygen's got an electronegativity of 3.5. So we subtract 3.5 minus 2.5. That's oxygen and carbon, and that gives us a difference of 1. So our bond polarity between carbon and oxygen is 1. We're going to add in our dipole moments, and we're going to see that oxygen and chlorine are both the more electronegative, so our vectors are going to point outward, and carbon is going to be the more partially positive one, so we add those perpendicular lines to show that. So now we can figure out then, is this going to be polar or non-polar? And this is indeed going to be polar. There is a net dipole moment, and the reason that there is because those magnitudes were not the same. Recall that our magnitude of bond polarity was 0.5 for each of the ones with carbon and chlorine, but it was 1 for carbon and oxygen. So that bond between carbon and oxygen is much more polar than the bonds between carbon and chlorine. So it's not going to fully cancel out. There is going to be a net dipole moment toward the oxygen. So the oxygen is going to be our more partially negative section of this molecule. So it will overall be a polar molecule. All right, let's look at one more. This is boron trifluoride, so boron bonded with 3 fluorines. And we've got our boron in the center, 3 fluorines around it. Let's look at those electronegativity values. We see that they should all be the same because we don't have anything else that we're bonding with it. So boron and fluorine right there. Magnitude of 2 then, as the difference is 4 minus 2 is 2. That's really kind of verging on being almost an ionic bond. But let's go ahead and draw our dipole moments, so our vectors, because fluorine is our more electronegative. I'm going to add our plus symbols in there to show that boron is the partial positive charge. So now, is this going to cancel out? Does everything have the same magnitude? Yes. Does everything have an opposite direction? It's kind of hard to tell with these molecules. What do you all think? So it is going to be nonpolar. These dipoles will cancel out. And part of what we need to know in order to see that is some kind of rules as far as vector addition. So when we're adding vectors and there's more than 2 of them, what we want to do is add just 2 of them together first and then add the 3rd or 4th ones. And so when you're adding vectors, you're essentially going to draw a parallelogram and then find the center between that. So what we'd want to do, we're going to find the addition of these 2 vectors right here. So we will, actually I'm going to kind of redraw them so they're a little closer for me. So like that. And now we're going to create this parallelogram between them. I'm just going to kind of use dotted lines to draw this parallelogram between them. And then I'm going to draw my vector here that is the addition of it. And now that I've drawn this, I essentially can get rid of these other vectors because we've added those 2 together and gotten this one in blue. And so now we're going to add this vector to that 3rd molecule, or the 3rd vector, and we can kind of see this one is going to cancel out because it is directly opposite it. So this vector will cancel out with that last remaining vector. So we can see that this is going to cancel out as a whole. So here's some more examples of molecules and whether or not they're polar or non-polar. So again, the two things that we need to look at is the magnitude, that value, and the direction that those vectors are pointing. So for an example like ammonia here in this picture, notice that the vectors are all pointing in. So the ones that we've been looking at so far as examples have them all pointing out. So because they're all pointing in, these are not going to cancel out. So this is going to make it a polar molecule. Our next example here with carbon bonded with 1 chlorine and 3 hydrogens, we can see that this is going to be polar because we don't have the same magnitude. That bond between carbon and chlorine is much more polar than the rest of them. As far as nonpolar, we really want to see that they all have the same magnitude, and if they all have the same magnitude, we want to see if they all have the opposite direction. If they do, then they'll cancel out to be nonpolar. A good rule for these is we want to look at the symmetry of a molecule. So looking at its shape and seeing, is it symmetrical? If it's symmetrical and the magnitude is all the same, it's usually going to cancel out to create a nonpolar molecule. So to be symmetrical, you'd basically be drawing kind of a dotted line down that center. And if you can fold it over and it's going to be the same thing on either side, that makes it symmetrical. And then it would usually be nonpolar. Alright, so up till this point, we've actually really been talking about still those intramolecular forces. So what was making something a polar or a nonpolar molecule? What was happening within that? But we needed to know that in order to talk about our intermolecular forces. So those are the ones that are between our molecules. And as you'll see kind of from this chart, depending upon the type of molecules, it can be different types of intermolecular forces. So it's depending upon if it's a polar or a non-polar molecule. As a general rule, though, overall, our intermolecular forces are going to be much weaker than those intramolecular forces. So let's take a look at those different intermolecular forces. So there's 4 main types: London dispersion forces, dipole-dipole, hydrogen bonding, and ion dipole. The first type we'll look at is London dispersion forces, which is named after Fritz W. London, who was a German-American physicist. And London dispersion forces can occur between all molecules. And these are a result of essentially the instantaneous and induced dipoles that we looked at earlier. So these are the fluctuations in electron distribution within a specific molecule or atom. So London dispersion forces happen due to these instantaneous and induced dipoles. So essentially what happens is we've got our electrons hanging out within an atom, and they at any one time might be on one side or another. In this example here, we've got 2 electrons that just happen to be right now at this moment in time on the left side of that atom. So that's going to mean that the left side of the atom has a partial negative charge, okay, because that's just where the electrons are, and the electrons are a negatively charged particle. That means the other side is going to have a partial positive charge. So what happens is if this specific atom of helium goes next to another helium near it, it's going to cause the electrons in that atom to kind of rearrange themselves so that their electrons can be closest to the side of the atom that does not have electrons in the first one. And so our first one, electrons move to the left side, so therefore this next one is going to line up so that its electrons can be near the side of the atom that did not have the electrons in it. So, and this happens pretty much as a chain reaction. So it's going to continue throughout this whole substance as one dipole induces another next to it. And these London dispersion forces then are going to happen between essentially these temporary charges. So as one side of the atom becomes positively charged, it's going to be attracted to the negatively charged side of another atom. And that force between it, I'm kind of drawing these dotted lines there, that's called our London dispersion force. So here's another illustration to show this. This is a diatomic molecule of chlorine. So chlorine's bonded to itself via a covalent bond. So that is a covalent bond there in the center. However, each molecule of chlorine, and again this is written as Cl2, is going to be then attracted to other chlorine molecules due to these London dispersion forces. And those are symbolized here by those dotted lines. So that's not a bond per se, but it's a force of attraction that's going to kind of hold one molecule of chlorine near another. All right, our next type of intermolecular force is a dipole-dipole force, and this exists in polar molecules. That's why we really had to look at what makes a molecule polar versus nonpolar. So we're specifically looking at a molecule that not only has polar bonds, but those polar bonds don't cancel each other out. So because each polar molecule has a permanent dipole, so we saw a permanent section that has a charged negative end and a charged positive end, it's going to interact with the permanent dipoles of neighboring molecules. Our dipole-dipole forces are stronger than London dispersion forces that we just looked at. And because polar molecules have both dipole-dipole and London dispersion, this is why our polar molecules will have a higher melting and boiling point than non-polar molecules. Essentially because there is more attraction between those individual molecules. So when we are changing from a solid to a liquid or a liquid to a gas, we have to put in energy in order to separate those molecules from one another. And if there's more forces at play holding them together, we need more energy to do that, which translates to a higher melting or boiling point. So here's a picture of a dipole-dipole. Again, this is happening in a situation where we have a net dipole moment. So we'll have these vectors showing us which way the electrons are going, which side of the molecule has the charged, has the negative charge, and which side has a more positive partial charge. So essentially the negative side of one molecule is going to be attracted to the positive side of another molecule. And this is going to happen all throughout the substance to create this dipole-dipole interaction. Remember though that this only occurs in polar molecules. So hydrogen bonds are our next intermolecular force, and these exist in polar molecules as well, but specifically polar molecules that have hydrogen. And we're looking for a hydrogen that's either going to be bonded with a fluorine, hydrogen bonded with an oxygen, or hydrogen bonded with a nitrogen. So essentially hydrogen from one atom is going to be attracted to fluorine, oxygen, or nitrogen on another atom. And this one is stronger than London dispersion forces and dipole-dipole forces. So here we've got a picture of our hydrogen bonds at play. Here are some water molecules. So water molecules is H2O. So that is a polar molecule, and it satisfies the prerequisites for a hydrogen bond because we've got hydrogen in it and we've got oxygen. So the hydrogen bond is going to occur right where those dotted lines kind of show it. So it's going to occur between our molecules. We've got the hydrogen of one atom is going to be attracted to the oxygen of another atom to create that hydrogen bond. And when the term hydrogen bond, it's not really a bond in the sense of a covalent or an ionic bond. It's not nearly so strong. In fact, it's only 2 to 5% as strong as a covalent bond. But it is a force of attraction that's going to keep that one water molecule near another water molecule. Our last intermolecular force is an ion dipole force, and this occurs when we've got an ionic compound that is mixed with a polar molecule. So the ionic compound will dissociate. Essentially that means it's going to break into its separate components. And then we've got the cation attracted to the negative end of a polar molecule, while the anion's attracted to the positive end of a polar molecule. And this is even stronger than a hydrogen bond. So again, this is what it's going to look like here. This is usually found in an aqueous solution, meaning you're taking some ionic compound and dissolving it in water. That would be an aqueous solution because water is our polar molecule. So water is polar, Therefore, it's going to have that positive and negative end. And we've got our vectors drawn in here on our water molecule showing that the oxygen is having the partial negative charge, the electrons are near it, and the hydrogens would have the partial positive charge. So suppose we have sodium chloride, that's table salt, and we put it in water. What's going to happen is the sodium chloride is going to separate out into sodium cations and chlorine anions. So charged particles for both of these, the sodium would have a positive charge, chlorine would have a negative charge. So here we've got this positively charged sodium in the middle of this picture, and it's going to be attracted to the negative end of water. The negative end of water is that oxygen. If we had the chlorine molecule shown here, chlorine would have been attracted to the hydrogen because chlorine's negative and the hydrogens are exhibiting a partial positive charge. All right, so then I asked which of these forces is the strongest one listed? And that answer is going to be hydrogen bonds. So hydrogen bonds are stronger than dipole-dipole. Dipole-dipole is stronger than London dispersion. Didn't list ion dipole on here, but that would be actually even stronger than a hydrogen bond. So again, our intermolecular forces overall are much weaker than our intramolecular forces. So the forces between molecules are weaker than the forces within molecules. When we're looking at those intermolecular forces, though, even those have different strengths. So our weakest would be the London dispersion forces that can occur between all types of molecules. If we've got a polar molecule, though, we can have dipole-dipole intermolecular forces, which are slightly stronger. And if we've got hydrogen and then either fluorine, oxygen, or nitrogen, we can have hydrogen bonding, which is even a little bit stronger. And then the ion dipole would be the strongest intermolecular force. That's if we took an ionic compound and dissolved it in a polar molecule such as water.